This is the Earth Science Classroom. Welcome back to the channel. So this video is in the playlist for both tectonics and volcanoes. Now we're looking at tectonic hotspots, which is certain locations around the world that have hotter magma material right under the lithospheric plate. And this video is going to discuss what is a mantle plume, where do these mantle plumes occur on the Earth, and how a mantle plume creates volcanism, and finally how this hotspot volcanism or intraplate volcanism is different to volcanoes that form on a plate boundary where they have a convergent plate boundary and one plate is subducting. So geologically, a mantle plume, or magma plume as it's occasionally known as, is a form of diapir. Now a diapir is a large amount or large volume of magmatic material that is either different to the surrounding rock through thermal properties, being hotter, or through the composition where it's just less dense and can rise based on density. So this large amount of generally magma, this large volume of magma, is under the surface, generally at the core mantle boundary, heated by the insane heat from the core, the outer core, and send in large volumes of magmatic material to rise up through the lower mantle or mesosphere into the asthenosphere or the upper mantle and go through the convection currents and on its way towards the lithospheric plate, which is the lithosphere and the crust, towards the surface, and that also create decompression melting, which will cause more of the rock around it to melt as it goes into an area of less pressure. So the liquid has an area to move. Now this diapir or plume has a tail and a connected pipe or continued volume of magma that is coming from the core mantle boundary up through the mantle and the layers up towards the surface, and it's connected, and at the head or top of the diapir or plume you're going to have this spreading out effect of the magma right underneath the lithospheric plate and send in magma into the plate and creating volcanoes on the surface. Now these mantle plumes are special because they are generally fixed in one geographic location under the plate around the world, and these may stay for an extended period of time. So this mantle plume could be feeding hot fluid magma, basaltic magma, and mafic magma from deep down in the lower mantle up towards the surface in a certain location around the world for in excess of hundreds of thousands, if not hundreds of millions of years, and feeding this volcanism on the surface from this mantle plume just below the plate. So locations around the world are both found in oceanic locations and on continents, and mostly oceanic because the oceanic plate is generally thinner. Even though it's dense, made of basalt, it's generally thinner, between 7 to 10 miles thick, compared to the continental crust, which could be in some areas of orogeny belts or mountain belts, could be as thick as 50 miles. So based on the plate thickness, the oceanic plate and the oceans around the world have more occurrence of these mantle plumes and volcanism occurring. So areas like the Southern Pacific, South Pacific, Northern Pacific, areas like Hawaii, the Galapagos Islands, Easter Island, and various areas around French Polynesia. Then look at the Indian Ocean and Reunion Islands, and the Atlantic with the Azores or Azores. Or on the continent you have areas like Yellowstone, which is a classic national park in the US, but also is a location of a massive mantle plume that has moved great distances since its formation or discovery millions of years ago. And the other location that's famous is in Africa, on the African continental plate, with the Afar junction, triple junction, caused by two large domes where the magma plume is pushing up under the crust, pushing the crust higher elevation, causing these two domes, the Ethiopian dome and the Kenyan dome. You can check more about those domes on my East African Rift videos. So at certain points around the world, as I discussed, like Hawaii and the Galapagos, you have this fixed mantle plume feeding hot magmatic material which is mafic in composition, that is basaltic magma, and it's feeding into the plate, into the crust, and flowing onto the ocean floor, and providing the ocean floor with this constant flow of magma and lava, turning into basaltic igneous rock and forming a volcano on the ocean floor. Now over time, that volcano is going to grow and develop as more and more lava comes out and forms into igneous rock, and it grows. Eventually it's going to reach the top of the ocean surface and go above the ocean surface and become a volcanic island. This island is going to grow as long as it's on top of the mantle plume, being fed this constant magma. And over the course of thousands of years, the volcano island is going to grow and grow into a large island series like the Hawaiian Islands or the Galapagos Islands or the Azores in the Atlantic. And the island that's on top of the plume is going to grow and develop, and as it moves with the tectonic plate in the direction of the convection currents, like the Pacific Oceans moving in a certain direction according to the oceanic crust, then that island, that volcanic island, will no longer be active and just become an island, and it'll move off the plume and it will just start to exist as an island, but slowly break down due to the forces of weather and erosion out in the exposure to the elements over a long period of time and the wave action, and that island's going to start to break down, and that solid basaltic rock is going to break down, and that island's going to get smaller and smaller and smaller until it eventually gets under the sea level, under the ocean, and become what we call a seamount. So an extinct volcano, a seamount, and it gets smaller and smaller and smaller, and you can see it through sonar and radar and satellites, but you see this long chain, a long sequence of currently active volcanoes over the plume, and then a long sequence, a chain of increasingly older islands and extinct volcanoes that have been moved by the plate motion, and a long sequence of these island chains that you can see. Now the classic one is the Hawaiian Islands and the Emperor Seamounts. You got this thousands of miles long chain of islands dating back 80 to 100 million years, and you see where some of the islands have actually been subducted at the edge of the Pacific Ocean, where it's going to descend underneath the continental crust of the Eurasian plate or the North American plate, but in particular the Eurasian plate, and be partially melted back into magma that's going to erupt through a continental volcanic chain or volcanic arc, and the cycle of the rock cycle is going to continue. But these amazing islands in this long chain and sequence, based on age and how fast it's moving off the plume and the current active volcanoes on the plume, are a fantastic way to see the progression and the history of this area and of the mantle plume, how long it's been there, how active it is, and how much it produces to create these large volcanic islands. So a mantle plume and intraplate volcanism. Intra means in the middle or inside. So in the middle of this massive tectonic plate, you have volcanism, and it's different to the volcanism that occurs on the plate boundary. Now plate boundaries come in three types. We know divergent, where you have the mid-ocean ridge or a rift valley, and you have convergent plate boundaries, where you have two plates converging towards each other, and you have subduction based on density differences of each plate, and you also have transform, where they slide past each other. Now, volcanism generally occurs with divergent plate boundary, where you have the lava coming out at the ridge, mid-ocean ridge, that Hess found in '63, and you also have volcanism that happens where one plate, the denser plate, is going to subduct under the subduction, or subducting slab will partially melt due to friction and temperature increases back down towards the asthenosphere, and you'd have partial melting of the subducting plate, but mostly the melting of the plate that's going to float on top generally is going to be that lighter, less dense plate, which is going to be continental or sometimes oceanic, and that's going to create magma that's going to rise up on the edge or coastlines of these plates and form either volcanic island chains on the boundary of the two plates, a certain distance away from their subduction zone, or more commonly, like the Ring of Fire, on the edge of continental plates, where you have this long chain or arc of volcanoes that are actually a certain distance and parallel to the coastline, which is showing you where the subduction zones are located and the trenches. So it's different because this mantle plume is a certain location and it's fixed, whereas the plate boundaries and subduction, you have this long chain that is, the volcanoes are usually fixed in location, whereas the mantle plume, the volcanoes can move with the plate, but the actual magma is in the same location. So there's some differences between the intraplate volcanism and the volcanism you get with plate boundaries. So in conclusion, a intraplate volcanism or a mantle plume is a stationary plume of magma rising up from the core mantle boundary, rising up through the mantle into the upper mantle, and reaches the plate, spreads out, and pours mafic basaltic magma into that lithospheric plate, creating volcanoes on the surface, whether it's ocean floor or volcanic islands, or pushing up the ground, the surface of the earth into a dome where the magma pushes up and it's going to increase the elevation of the above crust and cause domes like in Africa, or volcanism like you see in Yellowstone with the geysers and the flow of magma under the national park to create a caldera volcano. So there are certain key terms we know with plumes. It is that long tailed magmatic material rising up and creating volcanism on the surface.